So one of the more important applications of double integrals that we're going to look at that can be applied in physics, engineering, is going to be the center of mass problem and also the mass problem. So you may recall that a moment in a particular direction given a density function is given by these formulas. So we have a density function p of xy. The moment in the x direction is y times the density function, double integral of that. And then the moment in the y direction is going to be x times the density function, double integral of that. More importantly, we're looking to be able to find the center of mass of a given object. So if it's given a density function, three formulas that we're going to utilize. First, we're going to compute the mass. The mass is just the double integral of the density function across all points xy that lie on that plate or on that disk. To be able to find the center of mass, we're going to take 1 over the mass times the double integral of x times the density function. To find the center of mass in the y direction, or the center of mass of the y point, that's going to be 1 over m times y times the density function. It doesn't necessarily matter which of these you find, but you'd certainly want to find the mass first. So, knowing all this, let's go ahead and try to compute the center of mass of some given formula. Alright, so we have D to be a triangular region with three vertices 0, 0, 1, 1, and 4, 0. The density function is going to be P of x is equal to x. We want to find the mass and the center of mass of that lamina across the region D. We always want to make sure that we try to figure out what the region is that we're trying to find. So I'm going to graph it. So we have 0, 0 is one of the ordered pairs. We have the point 1, 1, which is another one of the ordered pairs of the vertices. And then finally 4, 0 is the third one. So what we have is we have this sort of triangular region. The first question we should answer is it type 1 or is it type 2? It could be either. However, if you make it one of the two types, it's going to be a little bit more work. If you recall back to the general double integral or integration of double integrals over general regions, you always want to try to make it so that one function touches another function. Clearly, if I were to go a type 1 or try to make this into a type 1 integral, I would have to make two separate double integrals because there's going to be one region to the left of this point 1, 1 and then another region that's to the right of that point 1, 1. So we don't want to make it a type 1 integral. However, as a type 2 integral, it seems like it's going to work very nicely because anytime I draw from left to right, it looks like that we're going to have one function touching another one. So we're going to have a type 2 integral to start with. The other thing we probably need to know is we need to know what the equations of the lines are because those are going to generate the bounds for us. All right, so we can go through and we can use the point slope formula if we know what the slope is. So let's just take the point from 0, 0 to 1, 1 first. Now, most of us can see that this is y equals x, but I just want to make sure that everybody can see that it is going to work out to be y equals x. So this is the line segment. I'm going to call that L1. First, you're going to get your slope using the formula y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Or in other words, that's going to be 1 minus 0 over 1 minus 0. So the slope of this first line segment, or the first line, is going to be 1. And then we just use y minus y1 equals mx minus x1. We can use the point 0, 0 for x1, y1. So we get y minus 0 equals 1 x minus 0. Or in other words, that's the line y equals x. So we already know that the first line, or the leftmost line, is going to be y equals x. Now we have to find the equation of the other line. Okay, we're going to do the same thing again. So for line 2, that's going to be the line segment from 1, 1 to 4, 0. To be able to find the equation, we're going to do the slope again. So slope m is going to be equal to, let's just use 1, 1 as x1, y1. Let's use 4, 0 as x2, y2. So that's going to be 0 minus 1 divided by x2 minus x1, 4 minus 1, which should work out to be negative 1/3. Now, we're going to go ahead, use y minus y1 equals mx minus x1. I'm going to use the point 4, 0 because it contains a 0. So y minus 0 is going to be equal to negative 1/3 x minus 4. Or in other words, we get the equation y is going to be equal to minus 1/3 x plus 4/3. So we go back up here. And this is going to be the equation y equals minus 1/3 x plus 4/3. Unfortunately, that doesn't help us too much because if we want to be able to do this as a type 2 integral, we need to get the bounds in terms of x because we're going from left to right first. Okay, so we know y equals x is already in terms of x. So what I'm going to do is I'm just going to solve this equation that we just got for x. I'm going to multiply by 3. So 3y is going to be equal to negative x plus 4. I'm going to subtract 4 from both sides. 3y minus 4 equals negative x. And then I'm just going to divide by negative 1. So 4 minus 3y is going to be equal to x. And then remember the other equation that we had was y equals x. So if we put all of this into a domain or some sort of region, the region D, if you go back up to the diagram that we had, notice that the line that's on the left is y equals x. Okay, so that's our lower bound. And then the other line, which we ultimately got, was that 4 minus 3y is equal to x. That's going to be our upper bound. So x going to go from y to 4 minus 3y. And then also y, we need to figure out what that range is going to be. Well, we can just go back up to the diagram. And it's pretty evident that y is going to go from 0 to 1. And we can see that because if you look at the diagram, the lowest point is 0, and then the highest y value, which is 1, 1, is going to lead us up to the y equals 1. Now we can set up a double integral to be able to find the mass first. Okay, so the mass m is going to be equal now to the double integral. Always take care of your variables first, constant second. So 0 to 1 is y, and then lower bound is y, and then the upper bound was 4 minus 3y. Remember the density function was x, and this is going to go dx dy. We're going to compute this. We're going to integrate. Our mass m is now going to be equal integral 0 to 1 x squared over 2 from y to 4 minus 3y. Then we still have our dy outside. We're going to substitute 4 minus 3y, and we're going to substitute y. I'm also going to factor out the 1/2 just for brevity. So we're going to substitute. So now we get 4 minus 3y squared minus y squared dy. Or, if we simplify that, that's going to be 1/2 the integral from 0 to 1. I'm going to FOIL this out, so we're going to get 16 minus 24y plus 9y squared minus y squared dy. And clearly this is just going to be 8y squared. So now we're just going to integrate term by term to be able to figure out what the mass is. So we're going to have 1/2 we're going to have 16y minus 12y squared plus 8/3 y cubed. That's an 8. Okay. And that's going to go from 0 to 1. When we compute, the 0 is going to go away. When we substitute 1 back in, everything's just going to become the coefficients. So we're going to get 1/2 of 16 minus 12 plus 8/3. And I'm going to throw that into my calculator just to make it easy on myself. And I get 10/3 for the mass. Alright. So I'm going to stop the video, and then in the next video what I'm going to do is I'm going to go ahead and find the center of mass utilizing this.